Okay. So, come back to this V12 and V21 for example, right. So, that this is actually this is point 1, right, and this is your lamp, right. This is I am drawing something like this. This is your lamp and this is your point 2. This is point 2. This is plus. This is minus. So, this voltage is your V12, right. So, if V12 is equal to say 10 volt, this is plus minus, therefore, V21 will be minus 10 volt, right. If you make V12, that is if this is plus, this is minus, if you make 10 volt, then V21 will be minus 10 volt. This is understandable, right. So, signs are used to represent the reference direction of voltage polarity. The voltage V12 can be interpreted, I told you this one, that best way this one, the potential at point 1 with respect to point 2 is V12. Therefore, logically it follows that just I told you that V12, if V12 is 10 volt, then V21 will be minus 10 volt. Therefore, V12 is equal to say minus V21. So, for the purpose of further explanation, come to the figure 1.7, right, two representation of the same voltage. You come here, right. For example, come here. So, here it is point 1, it is 1 and 2. This is a lamp. So, it is 10 volt. So, meaning is point 1 is 10 volt above point 2. This is the meaning, right. Similarly, if this is 1, this is 2. Now, polarity has changed. Suppose this is minus, this is plus. So, this has been minus and this has been made plus and this has become made minus. Therefore, say this one also can be there. This is a plus thing. So, point 2 is minus 10 volt above point 1. So, whenever you talk like this, you take plus as your reference point, right. If it is given like this, that means point 1, that is a plus terminal, point 1 is 10 volt above point 2, and here it is 2, here it is minus 1, but minus 10 volt, that means point 2 is minus 10 volt above point 1. Understandable, right, understandable. You will take this is plus terminal as your reference point, from there you will take, meaning is same. So, here it is point 2 is minus 10 volt above point 1, here it is point 1 is 10 volt above point 2, understandable, right. So, two equivalent representation of the same voltage V12, either this representation or that representation, both are equivalent to each other, right. So, whatever was there, that has been just now that has been explained. Therefore, this in general a voltage drop from 1 to 2 is equivalent to a voltage rise from 2 to 1, meaning is same. So, next is power and energy. So, power and energy calculation are very important in circuit analysis, because only current and voltage actually both do not serve all the purpose, because output may be power. For example, suppose at your residence the bulb is there, tube light is there, these are all represented by power. Therefore, voltage and current are useful variables in an electric circuit, but they are not sufficient by themselves. One reason is that useful output of the system often is non-electrical, and this output is conveniently expressed in terms of power and energy. And second thing is that output, so if you take any electrical elements or devices, their power output is maybe limited, maybe 40 watt, maybe 4000 watt, but it is limited, right. So, another reason is that all practical devices have limitation on the amount of power that they can handle. Just some devices, the specification is there. If you see anything, any bulb or any light or fan, you will find some specification is there, and one important specification is the power, right. For example, we all know from our experience that a 60 watt bulb gives more light than a 40 watt bulb, because 60 watt is powerful than 40 watt. We also know that when we pay our electricity bills, we are actually paying for the electric energy, that is watt hour consumed over a certain period of time, right. We that whatever electric bill we pay, this is watt hour. In general, little higher your higher values of unit, that is kilowatt hour, right. So, sometimes in English rhymes we define energy like this, that energy is power multiplied by hour, because if you look at that, energy is power multiplied by hour, because it is watt hour, 1 into hour, right. So, so we now relate the power and energy to voltage and current, because we have to relate now power and energy to the voltage as well as the current. So, power is the time rate of expanding or absorbing energy. So, power is measured in watts. So, mathematically P is equal to dW by dt. It is actually your what you call, that is a time rate of expanding or absorbing energy. So, it is P is equal to dW by dt, where P is the power in watts, right, W is the energy in joules, right, and T is the time in second. So, thus 1 watt from this equation, 1 watt is equal to your 1 joule per second, it is 1 joule per second, right. So, once again the power actually is measured in watts. So, mathematically this is P dW by T, and from the physics, the definition is power is the time rate of expanding or absorbing energy. Simply do not write the power is the time rate of energy, then it is not correct. Better you should write power is the time rate of expanding or absorbing energy, right. So, therefore, from equation 1.1 we have seen, right, I is equal to dq by dt and so on. Then 1.4 and 1.6, this equation is 1.6. Therefore, P is equal to dW by dt is equal to, we can write this equation dW by dq into dq by dt, right, and dW by dq we have seen it is V, and from equation 1.1 I is equal to dq by dt, it is I. From equation 1.4 it is your dW by dq is equal to V. So, P is equal to V into I, right. So, this is actually P is power. So, this is equation 7. I think I need not write it again, no, it is understandable that dW by dt, you write it in partial derivative, that your chain rule of the differentiation rather, that dW by dq into dq by dt, and dW by dq is equal to V, and dq, that is dW by dq is equal to V, that is from equation 1.4, and I is equal to your dq by dt, that is from equation 1.1. So, power is equal to voltage into current, right. So, equation 1.7 shows the power associated with basic circuit elements is simply the product of the current in the element and the voltage across the element. Therefore, power is a quantity associated with a pair of terminals, and we have to be able to tell from our calculation whether power is being delivered to the element or supplied by the element. If the power has a plus sign, this is interesting, this you have to understand. If the power has a plus sign, power is being delivered to or absorbed by the element. If power is a plus sign, right, or later we will see in the numericals another thing, you will be accustomed with this. And if on the other hand the power has a minus sign, right, that means power is being supplied by the element. So, but how do we know when the power has a positive or a negative sign, right? So, this is the question. So, polarity of voltage and direction of current play a major role in determining the sign of power. It is therefore, you are important to see this, right. So, this one, look at this one. This is a simple circuit element, say something it is, say it is something. So, this is plus, this is minus, right. So, current is, this current is plus, sorry, this terminal is plus, current is flowing from this direction, and here actually what we will do, that whenever a current you are entering the positive terminal, you will take the sign of current is positive. So, this current is entering the terminal, means from plus terminal the current is flowing. So, P is equal to V into I, right. So, that is why power is positive, that means this element actually is absorbing the electrical power. So, that means when I is leaving the plus terminal or entering into the plus terminal, right. So, not leaving, when it is entering into the your what you call this your plus terminal, that means current flowing in this direction. So, P is equal to V I. Now, it is actually entering the terminal, and when the current is leaving the plus terminal, you take minus sign. At the same time, you can understand that actually the current is going into the element from plus. So, current is your what you call entering into the plus terminal, and when current is leaving the plus terminal, it is leaving the plus terminal. So, current signs your symbol I, you will take your direction, it will be negative. So, P is equal to minus V I, V remains as it is V, but I the sign will change, it will be minus V I, right. This thing you have to add, this is absorbing power, and this in this case element is supplying power, because P is equal to minus V into I, right. So, one is entering into this your what you call plus terminal, another is leaving the plus terminal. So, when it is entering into the plus terminal, sign of current should be plus, and when it is leaving the plus terminal, it should be minus. These certain things, I mean basic thing, we have to keep it in mind, right. So, referent polarities for power using the passive sign convention. Now, in order to power have a positive sign, right, the direction of current and this red thing is nothing actually, right. So, direction of current and polarity of voltage must conform with those shown in figure 1.8 A and B. Now, whatever I told, right, by the passive sign convention, current enters through the positive polarity of the voltage, and this case P is equal to V I, because this current is entering through the positive polarity. Whenever current entering through the positive polarity, the sign I, that current your sign, it should be taken as a plus. That is why P is equal to plus V I, and in this case current this thing current is leaving the plus terminal, you should take minus. That is why P is equal to minus V I, right. Therefore, so by the passive sign convention, current enters to the positive polarity of the voltage, and this case P is equal to V I, that means V I greater than 0, right. So, V I greater than 0 implies that the element is absorbing power, and when P is equal to minus V I, right. So, element your what you call in this case V I negative, as figure B, the element actually is releasing or supplying power. Throughout the text or throughout this course, we will follow the passive sign convention. So, I suggest once again when we will, because later stage we will solve any problems and other thing. So, basic things should be initially it should be clear, right. So, that means when current enter into the positive terminal, I should be positive. When current leaving the your positive terminal, I should be negative. So, when it is positive, then it is element is absorbing power. When it is negative, element, this element minus V I means it is supplying or delivering power, right. That is why it is minus V I. So, passive sign convention is satisfied. I told you when the current enters to the positive terminal of an element and P is equal to plus V I. However, if the current enters through the negative terminal, then P is equal to minus V I. That means, if you look at the diagram other way, it is current entering through the negative terminal. Here also I have made I. Here it is another way is that current entering through the positive terminal, it is I. So, P is equal to plus V I. Current entering through the negative terminal, P is equal to minus V I. Otherwise, current entering through the positive terminal or leaving through the negative terminal. The way you can do is easiest way is current entering through the positive terminal, so it is plus V I. Current entering through the negative terminal, it is minus V I. Current entering through the positive terminal, element is absorbing power. Current entering through the negative terminal, element is supplying or delivering power. I hope you have understood this, right. This is required, right. So, in general we can write power absorbed is equal to minus of power supplied. Same concept like your the way to know I12 is equal to minus I21, V12 is equal to minus your V21. Similar way you can write plus power absorbed is equal to minus power supplied, because a power balance or energy balance equation always has to be satisfied. Now look at that figure, this figure 1. It shows two cases of element with absorbing power. If you look into that, here power entering into the current entering the positive terminal, this is plus, right, and this is the 5 volt. So what will be the power? V is equal to 5 volt, 4 is equal, and I is equal to 4 ampere. So power will be 5 into 4, so 20 watt, right, because current entering the positive terminal. Same thing you look, this is now we have made, this is 2 plus, this is minus, and it is here it is entering to the positive terminal, but here also if you look into that, current entering to the positive terminal, because current goes like this, and goes like this, right. So in this case your just hold on. So in this case, this is I is equal to 4 ampere. So this is that your what you call current going like this, this is 4 ampere. So current entering through the positive terminal, and in this case here also current entering through the positive terminal goes like this, this is also 4 ampere. So ultimately both the cases current entering through the positive terminal, but here it is 1 2, here also 1 2, but this has been plus, this has been minus. So in this case also P is equal to 5 into 4. So that means your what you call 20 watts. So both the cases element actually is absorbing the power, right. So both circuits apply, it is absorbing the power. So both the your what you call both the circuit actually absorbing the power. So I hope you have understood this, right. So both the circuit is P is equal to 20 watt, 5 into 4, here also 5 into 24. Only thing is that you see that current entering to that your positive terminal, here also it goes like this, I showed you. So little bit you you should understand this, then things will be easier for you in later stage. Now this one if you look, that two cases of an element with a supplying of power. In this case if you look, that current actually entering into the negative terminal. Just I for your this thing I will I will make it like this. For this one, this is 4 ampere. So current is going like this. So it is this direction is given here. So current actually entering to the negative terminal. So I should be taken as a negative. So P is equal to minus 4 into 5. So minus 20 watt. That means this element actually supplying the power. Similarly here also current is entering into the negative terminal. So it is going like this. So current entering the negative terminal, here also it is minus your, so this should be minus 4 into 5. So minus 20 watt. That means power is negative. So this element is supplying power, right, or delivering power, right. So just hold on. Right. So this is actually the minus 20 watt and minus 20 watt. So hope this one and this one concept is clear to you right from the beginning. In this course you have to if you your what you call, if you make this understanding is clear, then later stage you will find things are very easy. So there should not be any confusion or anything, right. So when you will go through this course and when you will see, if you have any doubt, you can put the question in your ask a question or in a forum. We are there to your what you call answer all your queries, but understanding is your more important. So now for any electric circuit, law of conservation of energy must be obeyed, right. For this reason, at any instant of time, little bit, I hope it is understand, it is your readable, you can make it. It must be obeyed. For this reason, at any instant of time, the algebraic sum of the power in a circuit must be 0. Therefore, we can write in general sigma power is equal to 0, sigma p is equal to 0. The meaning is, in a circuit you may have many voltage sources and many electrical elements, right. So sources, many cases power will be delivered and power will be absorbed. So total power delivered, right, and total, or in other way I can put that power delivered plus your power or delivered or supplied plus power absorbed is equal to your 0. So therefore in this case, in the case of power also, that your sigma p is equal to 0, that means summation of all the power. Later we will see how this your what you call this power delivered is equal to power absorbed, right, that we will see later. So, sigma in general summation is equal to 0. This is so this equation 1.8 it confirms the fact that the total power supplied to the circuit your must balance the total power absorbed, right. So, this is the concept, that way we write sigma p is equal to 0. This one we will see much later when I will take the example, I will do this. Now, to calculate the energy W supplied or absorbed by a circuit element between time say t0 and t, we integrate power. Therefore, we know that power is equal to your dW by dt, right. Therefore, dW is equal to, I am not writing, understandable, earlier we have seen the power is equal to dW by dt. So, dW will be equal to p dt. If you integrate, so W is equal to time t0 to 2 p dt, but p is equal to Vi, you substitute here p is equal to Vi, therefore, time is t0 to 2 dt, right. Therefore, this energy is the energy is the capacity to do work. So, energy is measured in joules. So, W is measured in joule, right. So, the electric power utility companies measure energy in watt hour or kilowatt hour, right. So, 1 watt hour is equal to 3600 joules. These are the standard this thing, you can keep it in your mind. Now, we will come to a few small example, right, small example. So, I hope up to this, before going to this few small example, I hope up to this you have your understood your what you call the basic concept, the current, the voltage, the power and the passive sign convention, right, and then in the case of power that your what you call that plus or minus, that absorb or delivered. Similarly, in the case of voltage, that which point is higher than the other point, one point is higher than higher point, other point, that for your voltage, all these things hopefully you have understood, right. Therefore, 1 hour is equal to 3600 joules, right. Now, come to that few simple examples, that how much charge is represented by 5524 electrons. This is example 1. So, each electron has E is equal to minus 1.602 into 10 to the power minus 19 coulomb, that we know. Hence, 5524 electrons will have minus 1.602 into 10 to the power minus 19 coulomb per electron into 5524, because each electron has this much of coulomb. That is why we are writing minus 1.602 into the minus coulomb per electron we are writing into 5524 electrons. So, total will be 8.849 into 10 to the power minus 16 coulomb, right. Here little bit has been cut for scanning. So, this is actually coulomb. Now, example 2, the total charge entering a terminal is, this is actually page number 17, given by q is equal to say 3t sin 2 pi t say millicoulomb, right. So, determine the current at t is equal to 0.4 second. A very simple thing, q is given. So, we know that I is equal to dq by dt. So, d dt of 3t sin 2 pi t, right. So, this is your 2 pi t. So, if you take the derivative of this one, so it is I is equal to 3 sin 2 pi t plus 6 pi t cosine of 2 pi t, that is milliampere, because it is actually it is in millicoulomb. So, that is why we are writing it is milliampere. So, at t is equal to 0.3 seconds. So, put here t is equal to 0.3 second. So, in this case I is equal to 3 sin 2 pi into 0.3 plus 6 pi into your 0.3 cosine of 2 pi into 0.3 milliampere. So, after computing this, you will get I is equal to 1.106 milliampere at t is equal to 0.4 second, right. I was here here actually here it should be your what you call 0.3, because here I have taken t is equal to 0.3. So, but here by while writing is it has been made 0.4, it should be 0.3. So, there should not be any confusion. So, here it is a screen, I cannot make correction here. So it is actually this one actually will be this one actually will be t is equal to 0.3. So, there should not be any confusion. So, that is why here we made t is equal to 0.3. So, next one is determine the total charge, the example 1.3. Determine the total charge entering a terminal between t is equal to 2 second and t is equal to 4 second. So, current passing through the terminal is given I is equal to 2 t square minus t ampere. This I is given, right, and time span is given to t is equal to 2 second to 4 second. So, by using equation 1.2, that we know I is equal to dq by dt, I is equal to dq by dt. So, dq is equal to I dt. So, q is equal to integration of I dt, but time limit is t0 to t. So, this is from equation 1.2, right. So, it is t0 is given, this is given to t is equal to 2 second and t is equal to 4 second. So, here actually t0 is equal to 2 second here, right, this is t0 is equal to 2 second and this is your t is equal to 4 second, right. So, it is 2 to 4 2 t square minus t into dt. So, if you integrate this, it will be 2 by 3 t cube minus t square by 2, limit is 2 to 4. If you simplify, right. So, you will get q is equal to 31.33 coulomb, right. So, next example is say 1.4. So, charge versus time for a given circuit element is you are given by q t is equal to 0 for t less than 0, right, and q t is equal to 2 minus 2 into e to the power minus 100 t for t greater than 0. You have to plot q t and I t versus time. Q t is already given, only I t you have to plot, I t you have to find out, then plot both, right. So, solution, we know that I t is equal to dq by dt. So, it is given q t is equal to 0 for t less than 0, right. Therefore, your it is actually, if you take the derivative also for t less than 0. So, actually whenever we take the less than 0 means it is something like this, the past history of the circuit, later in transient we will try to see this, right, there is past history of the circuit. So, that is why it mathematically represent, that is your what you call that t less than 0. So, in this case q t is equal to 0. So, for t less than 0, so this is 0, and when q t is equal to 2 minus 2 into e to the power minus 100 t, you take the derivative dq t by dt. So, here if you do so, then I t will be 200 e to the power minus 100 t for t greater than 0. Now, plot of q t and I t shown in figure 2. This is the plot of your q t. Q t already given, right, q t is already given, right. So, in this case, if t is equal to, if in this expression if you put t is equal to 0, right, then what will be there, that e to the power 0. So, actually 1. So, 2 minus 2 0. So, graph starts from 0 and right, and when t is increasing, it is in milliseconds. So, when t is increasing, finally it will reach to the steady state, that 2, right. When here when t is your increasing, right, t greater than 0, when t is increasing, say t tends to infinity, right. So, that means this term will vanish, only 2 will be there. So, that is why it is your slowly and slowly approaching, that is q t is coulomb, that is 2 coulomb, and this is the current, right. This is the current. When t is equal to 0, current is 200 ampere, because when t is equal to 0, this term is 1. So, it is 200. So, it is starting from 200, right, and when t is your increasing, when t is increasing, this current actually approaching towards 0, and when t tends to infinity, t is going to infinity, right, this term will vanish, it will be 0. So, at steady state current will be your 0. So, this is the plot of your this thing I t versus time, and this is your q t versus time, this is the plot. So, plot of charge and this is the plot of current, right. So, example, another example, say 1.5, the current flowing through an element is that I is equal to 1 ampere for t greater than 0 and t less than 1, and second thing is it is 3 t square ampere for t greater than, I mean when current time is in between 0 and 1, the current is 1 ampere, that is current is constant, and when for t greater than 1, it is 3 t square ampere. So, it is given. So, you have to find out the charge entering the element from t is equal to 0 second to t is equal to 2 second. So, this is the determine the charge entering the element from t is equal to 0 second to t is equal to 2 second. So, we know that q is equal to t 0 to 2 I dt, just we have seen, right, and t 0 to t 1 I dt plus t 1 to t I dt. That means, you have 2 time interval, this is a t 0 and this is t 1, t 1 is 1 second. So, 0 to 1, so t 0 to t 1. So, this is t 0 actually 0 and t 1 is 1 second, right. Another thing is we want in between 2 second. So, another is that t 1 to t. So, t 1 again is 1 second, this is 1 and t is equal to 2 second. So, 2, I hope it is understandable to you, because when you are understanding this t 0 to t. So, but you have 2 intervals, one is 0 to 1 and another is t greater than 1, but you have to find out in between 0 to 2 second. So, 0 to 1, that is t 0 is equal to 0 and t 1 is equal to 1, right, and then this one, then t 1 to t 1 is equal to 1, then 1 to 2 second and t is equal to 2, but this is I dt, this is I dt. So, this can be written as 0 to 1 I is equal to your 1 into dt, because this is given 1 ampere. So, I is equal to, in this case I is equal to, in between the interval 0 and 1 I is equal to 1 ampere. So, that is why it is 1 into dt plus in between the, and when t greater than 1 it is 3 t square a. So, 1 to t, 1 to, but we want in between 0 and 2 seconds. So, 1 to 2 it will be 3 t square into dt. This simple thing, but I hope you have understood this, right. When you will integrate and solve it, you will get q is equal to 8 coulomb. This is actually 8 c, 8 coulomb, right. So, I repeat once again for your understanding, because if you start in the very first year, that it is 1 in between 0 and 1, that is, this is t 0 is equal to 0, t 1 is equal to 1, but you have to determine the charge entering the element from t is equal to 0 second to t is equal to 2 second. But first you have to consider this, because 0 to 1, so this is 1 ampere. So, t 0 to t I dt and then t 0 to your what you call this one t 0 to t 1, then t 1 to t, right, t 1 to t, and then your is equal to the 0 to 1, in between 0 to 1 current is 1 ampere. So, 1 into dt plus that it is greater than 1, therefore, it is 1 to 2 3 t square dt, because expression is 3 t square, it is greater than 1, but we want in between 1 and 2, that means this 3 t square dt. If you integrate this, it will be your 1 plus 7, so 8 coulomb, right. I hope you have understood this simple thing. Now, another thing, another example is, this is actually page number 19 here. So, electrical energy is converted to heat at the rate of 8 kilojoule per minute in a resistor, your what you call, and charge flowing through it at the rate of 300 coulomb per minute. So, what is the voltage difference across the resistor terminals? So, electrical energy is converted to heat at the rate of 8 kilojoule per minute in a resistor and charge flowing through it at the rate of 300 coulomb per minute. So, what is the voltage difference across the resistor terminals? So, in this case we know that your V is equal to P upon I, right, that is the power, that means P is given 8 kilojoule per minute. So, it is 8 into 10 to the power 3, so 1000 joule per minute, and Q is given that 300 coulomb per minute. So, it is 300 coulomb per minute. So, that is 26.67 joule per coulomb, that is the voltage. Joule per coulomb is equal to voltage, we have seen earlier. So, V is equal to 26.67 volt. So, and another thing is, an energy source your forces a constant current of 4 ampere for 6 seconds to flow through a lamp. If 4 kilojoule is given off in the form of light and heat energy, determine the voltage drop across the lamp. So, it is telling that energy source forces your what you call a constant current of 4 ampere for 6 seconds to flow through a lamp, right. If 4 kilojoule is given off in the form of light and heat energy, determine the voltage drop across the lamp. So, total charge is Q, we know that I is equal to dq by dt. So, in general we can write that dq is equal to I dt. So, here we are writing delta Eq is equal to I into dt, right. So, delta EQ, so I is given 4 ampere, this is your 4 ampere the constant, and your time t is 6 second. So, delta t is equal to 6 second. So, 4 into 6, that is 24 coulomb. So, and the voltage drop, we know voltage is equal to that your potential difference is equal to dW upon dQ. So, here we are writing for this your in V is equal to writing delta W by delta EQ. So, it is given 4 kilojoule. So, 4 into 10 to the power 3 divided by delta Q, you got 24 coulomb. So, it is 166.67 volt. Now, 1.8, compute the power delivered to an element at t is equal to 4 millisecond. If the current entering its positive terminal is I is equal to 4 cos 100 pi t your ampere. So, and the voltage is A is equal to is given V is equal to 3 I one expression, another is given V is equal to 3 d I by dt. So, it is asked that compute the power delivered to an element at t is equal to 4 millisecond if the current entering its positive terminal is I is equal to 4 cos 100 pi t ampere and the voltage is V is equal to 3 I and V is equal to 3 d I dt, right. So, solution is simple, V is equal to 3 I. So, 3 into 4 cos 100 pi t, so 12 cos 100 pi t. Hence, the power is P is equal to V I. Listen one thing, this is we are covering in general, it is a DC circuit, DC course, but one or two simple example of your sine cosine function I have taken, and detailed sine cosine, detailed your in terms of sine cosine and single phase power or 3 phase power, that will come when the AC circuit. Here just to give you a feeling of that time function power and this thing, but later we will see that in single phase circuit will your power computation is different and 3 phase also something interesting, but here it is here simply it is given in terms of time function just to give you a feeling, but this is just to little bit of energy power, the basic concept. So, P is equal to, if you make V I, it will be expression, if you multiply all these two, it will be 48 cos square 100 pi t. But when t is equal to 4 millisecond, that is 4 into the power minus second, you substitute here t is equal to 4 your millisecond, then you will get P is equal to 48 cos square whatever it comes inside, you will get P is equal to 4.603 watt. Now, also another thing is given that V is equal to 3 d I by dt. So, it is 3 and d dt, d I is given here, expression of I is given 4 cos 100 pi t. So, here it is your I is equal to 4 cos 100 pi t, take the derivative, V is equal to minus 1200 pi sin 100 pi t. So, P is equal to V into I. So, this is the expression of V and this is the expression of I, 4 cos 100 pi t, you multiply, right, and you will get P is equal to minus 2400 pi sin 200 pi t. At t is equal to 4 millisecond, that is 4 into minus second, you put here t is equal to 4 into 10 to the power minus 3, you put it here, you will get it is P is equal to minus 4431.8 watt, that is minus 4.4318 kilowatt, right. So, up to this some more example we will see later. So, up to this it will give you some feeling, but regarding time variation of current and voltage, but all time variation other things we will see for single phase thing, but this is only first will be considered a DC circuit, basic concept, then basic laws, basic theorems, right, DC transient, the first order circuit only, and next will your what you call, but these are the power cut your current, everything taken in time, such that will give some flavor in the at the beginning, right. So, thank you very much.